All right, so this problem is a experimental analysis of a cart colliding with a force sensor, and then various graphs are made, and we have to determine some information from those. And so the key to making this problem sort of doable is recognizing there's multiple ways to approach these. So you can do stuff with Newton's laws, or you can use momentum and impulse. So the first one in part A, we have to figure out the average acceleration. And the key word in this is average, right? Because the velocity graph is complicated, right? It's not a linear or a constant or even a quadratic function. It's something more complicated. But the average acceleration is pretty straightforward to get, right? So by definition, the average acceleration is the delta change in velocity rather than the d change in velocity, right, over a finite period of time, delta t. And all we really care about is that time interval from 0.37 to 0.33, or 0.33 to 0.37 seconds, that 0.4 second range. And I can get that velocity before and after just by looking at the graph. So delta v is v final minus v initial. If I look at the velocity at 0.37 seconds, I would read a number that looks something like negative 0.18 meters per second. And because it's between tick marks, you could interpret that differently. You might say it's negative 0.17, you might say it's negative 0.19. It's clearly closer to the negative 0.2 than the negative 0.1. So any number between negative 0.15 and negative 0.20 would be accurate for the purposes of this. It's an estimate, because it's from the graph. And so that's v final, and we subtract v initial, and at 0.33 seconds, I can see that we're somewhere between 0.2 and 0.3, and I'm going to go with 0.22 in this case. And delta t is 0.37 minus 0.33, or 0.04 seconds, right? That's going to be an average acceleration. If I wanted an instantaneous acceleration, I'd have to tell you to take a derivative, and if I didn't give you the function, you can't do that. You could sketch it on the graph if that was what was asked for, and measure the slope that way, or approximate it, but it's only asking for an average. So, I get that, and if I compute it correctly, I'm going to get an acceleration of negative 10 meters per second squared with those numbers, right? If you pick slightly different numbers, you're going to get slightly different results. But something in that range, based on the data, is the way to go. So for parts B and C, they're kind of solved together, and there are multiple ways you can approach them that are all kind of variants of the same thing. What I'm going to start with is what I think is the most obvious way to do that, to figure out part B and C. But there is another, so I'll do that one second. So first, we're trying to figure out the magnitude of the change in momentum. And if I'm asked about a change in momentum and I see a force versus time graph, I immediately think of the equation J equals delta P. And since this is what I want, if I can find the impulse, which is the area under that graph, then I can solve it. So if I recognize this, then I also recognize this is area under f of t versus t graph, right? And so at that point, now I just need to figure out the area of that graph. And it's not trivial, because it's kind of a, it's not a simple function, but it's also just triangles, right? The graph looks something like this, right? And so if we split it up into pieces, first thing I recognize is that these green sheeted areas are each half a box, right? Next, there's two blue boxes, right? And then finally, I recognize that I can calculate the area of this triangle, right, with a 1/2 base times height. And then double it because there's two of them, right? So if you do all that carefully, then you figure out that the area is 0.6 Newton seconds. And so since that's the area, that means delta P is 0.6 Newton seconds as well. Okay. And so once you have the change in momentum, calculating the mass is fairly straightforward because we're just going to use that same relationship and substitute the definition of momentum in, right, which is the next slide here. So delta P equals m delta V, right? Mass is not changing in this case, only the velocity is, equals 0.6, right? And we found delta V in part A, right? That was part of our acceleration calculation. So this is going to be m is 0.6 over 0.4, which is 1.5 kilograms. So that's the way that I think is most straightforward. But you could also do it backwards in some sense. Remember, we also talked about if we have a force versus time graph that looks something like that, there's an average force that sort of describes the same motion, right? The integral of f dt is the same as saying f average times delta t, right? So if we take that approach, then we can use, even though we kind of have to find area anyway, we can instead really think of it in terms of a force. And so if we calculate what this value of f average must be by calculating, right, that this rectangle, this blue rectangle, has to have the same area as the red sort of mixture of triangles thing, we can calculate f average. Again, I'm pretty sure you're going to find by doing that you found the area, and so you've already done, in some sense, what part B asked for. But if you do that anyway, you get that the average force is about 15 newtons, right? And since we know F equals ma, we found the average acceleration, so we could just average statement on both of these, right? And we know this, and we know that, so we can solve for m first, which is going to give us a 15 over 10, right? Because we're doing magnitude, so I do the absolute value. And this is also 1.5 kilograms. And then we can go work backwards, right? So if we have the mass, right, we're going to use that same relationship, just working exactly backwards, and we'll get that delta P is, again, 1.5 times 0.4, which is 0.6 Newton seconds, right? It works backwards or forwards. I think the first way is simpler because if you want to figure out this calculation, you really need to already find the area, and so if you just remember what the area means, you're already done with that. You're sort of like doing more work in that second method, but both work. And so finally, this last part is an energy conservation one. And it's just remembering definitions, right? We want the change in energy of the cart. And in this case, it's not going up or down any hills. There's no spring, so the only change in energy is the change in kinetic energy from the change in velocity. And so this is going to be just that. Oops, I wrote an extra minus sign, or an extra line there. There, minus, right? And since the mass doesn't change, then we just do that. And we found the mass already. That's the 1.5 kilograms, or whatever you calculated. So if you get it wrong in part C, you don't get it wrong a second time. And then these are just from the graph, whatever you found in part A. Right? And so if you plug that in very carefully, you get 0.012 joules. And that's it.